Hello, going to do this Unit 7 review for circular motion stuff. There's going to be a whole bunch of equations at the top of your test that you'll be able to use, and just want to make sure you know what those are. You're going to have, of course, unbalanced force for circular motion is mv squared over r, and since force is mass times acceleration, that means mass times this must be the acceleration of those two. When something's moving in a circle, the speed of it is 2 pi r over the period, then time it takes for one lap. And sometimes we need, I don't think we need it on this review, but you know those problems where the car is going around driving in a circle, not over the hill or in the valley. That's, you don't need that. But if it's driving around a turn, you might need that force of friction equation. And I think I'm going to leave that, and then I'll write the other equations that are going to be up there for universal gravitation stuff when I get to number 8. All right, so that's what you can expect to have to work with. At the top of the first hill up here at A, 60-kilogram passenger feels as if she weighs. Why is that in quotation marks? Because her actual weight isn't going to change, but she will feel heavier or lighter depending on where she is on the track. Explain which force provides the sensation of weight. Sensation of weight, how heavy you feel, in other words, is the amount of normal force on you. Now, usually, if you're just like sitting somewhere, just standing, whatever, that's exactly equal to the force of gravity. So we think of our weight as gravitational force, and that's true. But the sensation, like our ability to feel our weight, is the force pushing up on us. If there was no force pushing up on you and you were just like free falling, then you wouldn't feel your weight. Explain which, how fast is the roller coaster going over the 3-meter radius hilltop to create this sensation? Okay, well, she's going over the top of a hill here at A. I'm going to make a force diagram. At A, the center of the circle is down here. Sorry, it's probably a smaller circle than that. So that means down toward the center of the circle is the winning direction. So I've got the force of gravity winning and the normal force losing. Now I know that the normal force on her is 500, and I know that the gravitational force on her is her mass times 10, so that worked out well with for the winning and losing, right? So unbalanced force is equal to the force of gravity minus the normal force. And when I have circular motion, I know that mv squared over r is equal to the unbalanced force. So I'm going to substitute that in here. M, her mass is 60. How fast, that's what I'm looking for, the v. So v squared over r is equal to 600, that's the gravitational force on her, minus 500. So time to do some math. I think that v is going to be equal to, this is 100, and then 60 divided by 3 is 20, so 100 divided by 5, so the square root of 5. So that roller coaster car must be going at about 2.2 meters per second. All right. At point B, the roller coaster has reached a speed of 28 meters per second. How large must the radius of the valley be so that a 100-kilogram rider will experience a normal force 5 times their weight? So that means that normal force, their weight would be 1,000, right? This times 10. So 5 times that is 5,000. Draw a force diagram. Okay, so we're here at in this valley now. So the circle here, the center is up. So that means that, of course, I've got my force of gravity going down, and it's the same as it would always be on this person, because gravity doesn't care. And then, since the center of the circle is up here, that means up is the winning direction. And we want 5 times their weight. 5 times that is 5,000. All right, and so I'm going to write my unbalanced force is equal to, this time it's normal force minus force of gravity, because that's the winning direction, because the center of the circle is up here. So unbalanced force is equal to mv squared over r. mv squared over r. How large must the radius be? So that's what I'm looking for here. Is equal to normal force minus force of gravity. All right, just have some math left to do here. So r is going to be, if I do that subtraction, that very difficult math, 5,000 minus 1,000 is 4,000, and then I'm going to swap these, right, and multiply the r up to here, divide by that, because that's how math works. So r is going to be equal to 100 times 28 squared over 4 grand. I'm in scientific notation mode, so that means 19.6. That is because of the gravity kind of problems that we'll see later. If I want to get back out of that mode and just go to normal, I can do that, and then just hit enter again. So 19.6, or about 20 meters, I'm going to call that. Okay. At point C here on the side of the loop, so now if they're on the side of the loop, the center of the circle is over here to the left. Traveling 20 meters per second, 7-meter radius curve, draw a quantitative force diagram for the rider. So here, of course, we have the force of gravity, and that's going to be 700 newtons. And then there must be a force toward the center of the circle. What is that force? Well, that's the normal force. Why is it pointing to the side? Because the track can only push perpendicular to the track, so it's going to be pushing toward the center of the circle. And if you're tempted to put a force up here, there wouldn't be, and then you're like, wait a minute, aren't these supposed to be balanced in this direction? No, because this, as the car goes up the loop here, it would be slowing down, so that would just be down here slowing it down, and then this would be the force toward the center of the circle. They're traveling 20 meters per second, 7-meter radius curve, so the unbalanced force, this is the only thing toward the center of the circle. This is not toward the center of the circle, so it's not part of this equation, because it's not toward the center of the circle. Let's see. Unbalanced force is mv squared over r, and that would be equal to the normal force. And to make a quantitative force diagram, that's what I'm missing, what that number would be equal to. So that's 4,000. So that person's feeling a lot of G's, right? This is how heavy they usually feel. So if you want to know how many G's they feel, I think I put this equation down here for you. You just have to take your normal force, divide by your gravitational force. So in this case, that would be 4,000. This problem does not ask you to do this, but I'm just going to do it for fun. So they're feeling about 5.7 G's going up this turn of force pushing toward the center there. All right. At point D, we're at the upside down at the top of the loop now. So it's upside down at the top. There it is, upside down at the top of the loop. How fast would the train have to pass through the 4-meter radius curve to produce a 200 Newton downward normal force? Like downward normal force, well, they're upside down here. Oh, the track can only push down there. So what does that mean? What does a diagram look like? Got the force of gravity, and then the normal force is also pushing down. So I'm going to put that right next to it there. There are two downward forces. 40 kilogram child, so the force of gravity would be 400 newtons. And the normal force, they're telling us that it's 200. And we're also given here that it's downward, just in case I didn't get that. So here, the unbalanced force, there's two, the center of the circle's down here, so both of these are in the winning direction. So force of gravity plus normal force. I mean, that's a lot of the problem solving here. If you look at the different unbalanced force equations, just figuring out exactly what forces are winning, losing toward the center of the circle. That is absolutely key. All right, so unbalanced force is equal to mv squared over r. So m v squared, don't know what v is, how fast, that's what I'm looking for, over r is equal to force of gravity plus normal force. So that's going to be 610, so the square root of 60, about 7.7 meters per second. All right, I'm exiting the loop at valley E. So now the center of the circle is up here. The 2,000 kilogram, track, I'm sorry about that. That should say car. That is a mistake. The 2,000 kilogram car exerts a normal force on the It's a normal force on the roller coaster. Oh, this is all mixed up. Sorry, I did a little editing here and I completely botched this question. So if my confusing, very confusing wording caused a problem for you, let me fix that and then you can pause and try this again. So exiting the loop, what I'm trying to say here is that there's a normal force of this pushing up on the car. That's what I'm trying to say. And I'm sorry for any confusion that bad wording caused. Or maybe, you know what, maybe before you get to this, I'm doing this video before you actually get this, so maybe I'll try to fix that. Maybe the version that you get will be fixed. I'll try to remember to do that. So track has, the radius is now 130 meters. Draw quantitative force diagram. Okay, so make my force diagram over here. The center of the circle again here. This is a big circle with the center up there. So winning direction is toward the center. So normal force is winning versus gravity. It's a 2,000 kilogram car, so gravitational force must be 20,000. And the normal force is 90,000. And the radius, I guess what I should have asked you here, and I'll add this, I'll fix this also. Draw a quantitative force diagram for the roller coaster car and find the speed at E. I'll figure out how fast it's going there. So that should be fixed up by the time you see this, I hope. Unbalanced force is equal to winning minus losing. Unbalanced force is m v squared, looking for that v again, over r is equal to normal force. Sorry, it's an extra dot there. Doesn't mean anything. Okay, so that's 70,000 and then I'm going to have to multiply by 130. Right, that's going to multiply up to there, and then I have to divide by 2,000. I'm doing that all in one calculation. Looks like this. I have to take the square root of 70,000 times 130 divided by 2,000. That's some math for you right there. So 67 meters per second. Right? I mean, that's when you expect you to be going fastest after you come out of this loop and you're zipping along there. All right. At the top of the hill F, the roller coaster crests the 5-meter radius curve at 6 meters per second. Draw a quantitative force diagram for a 60-kilogram passenger. How many G's would the passenger feel at the top of the hill? And just in case you haven't figured that out, that's how you do it. Normal force divided by gravitational force. That's how many G's. Okay, so at the top of the hill, the center of the circle is now down. That means that gravity winning, normal force losing. If you're wondering to yourself, how am I supposed to know when the normal force is also pointing down? When you are upside down, that's when. This is just going over a hill. So let's see, quantitative force diagram for a 60-kilogram passenger, so that's going to be 600 newtons there. And I know that unbalanced force, in this case gravity winning, normal force losing. Unbalanced force is m v squared over r is equal to 600 minus the normal force. And the normal force here is the thing that we don't know. So the normal force would be equal to, if I add that over to this side, and then I would have to do 600 minus that. So 600 minus 60 times 6 squared divided by 5 is 168. And then if you want to know how many G's you're going to feel, you do normal force divided by gravitational force. So that'd be the 168 divided by 600. So 0.28 G's. What does that mean? Well, if you're feeling less than, like 1 G is like normal, right? If your normal force is equal to your gravitational force, then normal force divided by gravitational force would be equal to 1. That's 1 G, that's like normal Earth gravity. If you're feeling more G's than that, that means you feel heavier, and if you have less than 1 G on you, that's when you feel lighter. All right. Car travels over a hill at a constant speed if the radius of the hill is 30 meters. At what speed would the unbalanced force equal only, I'll have to fix that too, that's not a word, only the force of gravity. If the car were to exceed the speed, what would happen? So at the top of the hill, this down here is the center, so that's the winning direction. So gravity would be winning, and the normal force would be losing, but this says, what speed would the unbalanced force be only the force of gravity? So in other words, the normal force here has gone all the way down to 0. So that is the maximum speed that this car can go over this hill without going like Dukes of Hazzard on, and getting airborne. This is like a ramp, right? So there is some speed that will be too fast and the car will actually leave the track. So that's what we're trying to find here. So that's kind of the answer to this question here. If the car were to exceed the speed, what would happen to the car? It would go airborne. Does airborne have an E on the end of it? I don't know. Ask your English teacher. So force of gravity on this car. If you're wondering, well, what about the mass of the car? Well, let's see what happens here. I don't know the mass of the car. You could make one up if you want to, but I'm just going to put it in as M there. So if this is the only force acting toward the center of the circle, so here, mv squared over r, I don't know the mass of the car, m v squared over r is equal to the force of gravity, which is 10 m. And looky there, the m shows up on both sides, so excuse me, I didn't actually need to know it. V squared would be equal to 300, so the square root of 300 is 17 meters per second. That is the maximum speed that the car can go over this hill without going airborne. If you look back at the different force diagrams, I think I gave you an example of every possibility. So here's gravity beating normal force because the center's down here. Here's normal force beating gravity because center's up. And here's gravity and normal force in the same direction, both down. A couple other examples of normal force winning, gravity winning, and number 6. And then here's one where the normal force has dropped to 0. So I think that's all the different examples that you could get. And and also normal force is the only thing toward the center. So a lot of different possibilities, but if you just keep them straight, you've tried them all. Okay, what about universal gravitation problems? What are the equations that we're going to get here? We're going to get Newton's law of universal gravitation. Sometimes you could write it as M1, M2, whatever. A lot of situations, excuse me, there's a bigger object in the middle of an orbit, and this is the smaller m, so see it written like that sometimes, but however you call those m's, that's how we do that. You know that g is equal to 6.7 times 10 to the negative 11th. Have that stored in your calculator to make things easier. When something's moving in a circle, we know, oh, I already put that one on there. The v equals 2 pi r over t. And velocity of something in a circular orbit is the square root of gm over r. I think I put that one on there for you. And period squared is equal to 4 pi squared over gm. This is the mass of the thing in the center, not the thing in orbit, times r cubed. So you get those equations too. Okay, using the principles of circular motion, find the force necessary to keep the shuttle in its circular orbit around the Earth. All right, well, so here, that unbalanced force would be equal to, I think I know all these things, right? So the shuttle is 94,800 kilograms times v squared over r. Now this is, just be careful here, the radius of the orbit, here's the Earth, radius of the Earth, and then this, the shuttle orbital height above the Earth. This is something that many students of mine, and I'm sure in other places too, this is the altitude here. So to get the radius, they forget to do this, to add these together. The radius of the orbit is radius of the Earth plus this, because that's the radius of the circle that the shuttle's moving in. So mv squared over the r is going to be the sum of these. All right, so let's crunch those numbers. 94,800 times 7823 squared divided by, I probably should have used the little fraction thingy, but just put parentheses there and I'll be okay. 6.38 times 10 to the 6 plus 2.76 times 10 to the 5th. And that should do it. Give me about, I'm going to do two significant figures, so I'm going to call that 870,000. You can, if you're using one of these calculators, go into your mode, put it in scientific notation mode, and then it does that for you. And you do 8.7 times 10 to the 5th. You can also, I wonder if you knew this trick, you can tell it how many significant digits you want. So if you want 2, then, oh, that gives me 2 after the decimal. So if you only want 1 after the decimal, then you can change that to 1 and it would say 8.7. So that's what I want here, 8.7 times 10 to the 5th newtons. And now, find the gravitational force that the Earth exerts on the shuttle. So now we're going to do it this way. But if you made a force diagram, like the gravitational force is the unbalanced force, so these two should be, how do they compare to each other? They should be equal. If this is all the right numbers, if this is for real, and it is, we looked all this up, then we should get the same thing. So this is equal to gm of the Earth times the mass of the shuttle over r squared, and the r is the same thing we did there. I'm going to get a nice fraction this time. Just make sure that I have my g stored in there. I do. So I use 6.67 instead of 6.7. I don't care which you use. It doesn't matter. Should still be good to 2 decimal places. So let's see. Let me set that to what I want, 1 place after the decimal. And I'm going to bring up a fraction to put all that into. And I'm going to put in g times the mass of the Earth times the mass of the shuttle divided by the radius, which is that sum that I did right here. That's 6.38 times 10 to the 6 plus 2.76 times 10 to the 5th. And don't forget to, in this equation, that r is squared. All right, that should be it, and hopefully get the same thing. Oh, well, because of rounding and whatever, we got 1 tick different, but they should be equal to each other because that is the unbalanced force toward the center of that circle. And that is your review in under 30 minutes. No free pizza.